Okay, well, thanks, I guess, for sticking around. So, yeah, my name's Josh Pulsipher. I'm a professor of chemical engineering at the University of Waterloo. And I've been doing stuff with Julia and JuMP and InfiniteOpt for quite a few years now. So it's kind of taking this opportunity to kind of give an overview of a lot of different projects that we have going on now. I have basically a team of students now, so now we have a lot of stuff that we have going on. So this is kind of a catch-all review of some recent progress. Okay, but first off, so what is infinite dimensional optimization? That's what the infinite stands for in InfiniteOpt. Well, basically, we have variables or constraints that are indexed over continuous sets. So giving you an infinite number of decisions that you need to make, or an infinite number of constraints. And that's what that is. Essentially, we're optimizing functions. We could have called this function opt, but InfiniteOpt sounds cooler, so that was the clear choice. So three common domains that might be indexing your variables include time, so if you have dynamic optimization, space, commonly in some sort of PDE-constrained type formulation, or uncertainty, so you can think of having random scenarios in like a two-stage stochastic program or something like that, or combinations of the above. So during my PhD, we kind of came up with kind of a unifying modeling abstraction to capture formulations from those different classes of problems, and kind of coming up with some sort of unified language to represent them, since they each kind of do slightly different choices. So we have what we call infinite parameters, which are the parameters that index the variables over the continuous spaces, like time, space, uncertainty, that then give us infinite variables. We can have differential operators, so like derivatives or things they might use to make differential equations or stuff like this, or Laplace operators, and measure operators that can help us summarize the resulting infinite dimensional variables and expressions. So this gives us a framework to model problems across a wide range of optimization fields, and this is the abstraction that is behind InfiniteOpt. Okay, so this InfiniteOpt gives us a way to model these types of problems, but we need to solve them. The way we think of doing that is with transformation. So one of the more common ways of doing this is using a technique called direct transcription, essentially discretization, where you choose either a single or a combination of different numerical methods, and you project your infinite dimensional problem onto a finite number of points, giving you a finite dimensional problem that you can solve with typical tools like JuMP. But because we've modeled it kind of in its original infinite dimensional form, you don't necessarily have to solve it that way, and we're also investigating other types of solution techniques like projecting onto functions or something like that to also give you a finite dimensional problem to solve it that way as well. So we're kind of decoupling the formulation from the technique you used to ultimately solve it. The advantage of this, I've shown this slide a few times, but basically you can think of a bunch of different applications that come up in like dynamic, PDE, and stochastic optimization, and this kind of gives us one framework to kind of model them all in one place. And so this is just showing some of the applications we've done in my research group. So InfiniteOpt then, the package. This is the Julia package that extends JuMP to implement this modeling abstraction, helps us capture the wide envelope of problems, and it automates a lot of transformations, namely different types of direct transcription to solve these. And it's helped us kind of inspire some new ways of modeling these types of problems. I'll go into that in just a little bit. And because it's in Julia, kind of like JuMP, it gives us a very compact, and I would argue a very intuitive modeling interface for these types of problems to pose stochastic and differential equations and integrals quite compactly and naturally. We'll also talk about this a little bit more today, and I talked about this last year. It helps us accelerate solutions, so we can leverage the unique structure of these problems to accelerate their solution, for instance, on GPU, using MAT-NLP, and solve these very efficiently. We've put quite a bit of work and time into the documentation and tutorials, maybe not quite to the level of Oscar, but we have pretty good documentation to help people pick this up and use it as well. This is always a little bit dangerous to do, but I thought this year I'll go ahead and do a comparison of kind of how we compare against some of the other tools that are out there. So I have Py1DAE, which is probably the closest to what we do, Casati, Gecko, optimal control, GPROMs, which is more common in chemical engineering, and modeling toolkit. So they all handle problems with ODEs, which comes up often. For PDE type support, not all of the tools support those, but PyOmo and InfiniteOpt do, along with modeling toolkit, although they have some limitations. For stochastic problems, InfiniteOpt is the only one that's kind of encompasses those as well. Most of them are free, with one exception. A number of them are extensible. I mean, there's an API to extend their capabilities. This is especially easy when Julia, because of multiple dispatch, makes it quite easy to plug in more functionality. So ML models, this is referring to being able to embed machine learning models. We'll talk about this a little bit more today. InfiniteOpt does provide that ability, as does Gecko. Some other packages don't directly do that, like Py1DAE doesn't directly support that, but you could try to hack in Omelette and kind of make it work, which is why it's yellow there. In terms of GPU support, basically InfiniteOpt and optimal controls are the main ones that provide that functionality. Modeling toolkit, in theory, you could kind of port it to something. That's a little fuzzy, so that's why it's in yellow. And then measures, this is kind of referring to supporting integrals, risk measures, and stuff like that. And you can kind of see how that stacks up as well. So this is kind of how InfiniteOpt compares to some of the other packages that are out there. I think what kind of makes us unique is the breadth of problems we support and some of the solution capabilities that we have as well. So with that wider breadth of problems, what this has done as well is, as we put everything kind of in one space, it has kind of inspired some different ways of modeling and solving problems. And so this is just one slide on that. So one thing we did is we took chance constraints, which come from stochastic optimization. And in this space, we kind of figured out we could take an analog of that and actually apply it to some deterministic dynamic and PDE-constrained optimization problems to give us a nice way of intuitively relaxing constraints, kind of an alternative to soft constraints. So we have a paper on that. We call those event constraints. We did something similar of risk measures, again, applying them to deterministic problems and having like alternatives to the bolt subjective and stuff like that to have different ways of shaping dynamic trajectories. As well as we're combining uncertainty in space and time. I'm starting to think of natural ways to capture that uncertainty, and there's random field theory. And so we've looked into using random field theory to motivate optimization problems. We call that random field optimization. So we have a paper on that as well. And now we're looking a little bit more into using surrogate models that are especially well suited for continuous infinite dimensional type problems. So looking at like neural operators and stuff like that. And so we have some initial work there, and we're hoping to take that a little bit further. Kind of a timeline of things that have happened. So I first kind of started working on this in 2019. We released the first version of it shortly, like I think 2 weeks before the pandemic started. So that was exciting. Then the pandemic started, and we had more time to do it, so we refactored it. Got version 2. Added derivatives, so we kept adding more functionality. Got to 0.4. Then I graduated and then did a little bit more during my postdoc. And then that's kind of where we left off last year. Well, there's some other stuff in the background, and then we've been getting on just a lot of functionality over the last few years. Still not really releasing since 0.5, and finally, as of a few weeks ago, we finally released 0.6, so we kind of did a lot of refactoring and added a lot of these different functionalities we'll go to in a little more detail in a few slides. So we've finally released 0.6, we have a lot more features that have come with this. So what's new in 0.6? This was the changelog for 0.6. This is just all the changes and additions we made. I'm not going to enumerate them all, but quite a lot of stuff went into it. And so I'll just kind of go over some of the highlights. And this is the changelog. So we, I guess, added 15,500 lines of code and took away 17,000. So it's a pretty extensive update. With that, kind of looking at the code base, so I looked at the tracked lines we have on our CI. So if you kind of go to the various versions we've had over the years, we've kind of steadily grown the number of lines of code we have as we've added features. Kind of makes sense. But then we kind of made a concerted effort as we were adding features to 0.6 to try to simplify the code base and kind of make it a little bit easier to work with as I'm getting more students trying to take this up, trying to simplify the barrier for entry. So we actually decreased the number of lines we had by about 600 lines of code, and we have a lot more features. So more features and less code was kind of a nice outcome that we got with our recent work. Another big change we had is this paradigm we use to go about solving models in InfiniteOpt. So before, we had this paradigm that we called optimizer model. So essentially, your infinite model would be translated in some way to a JuMP model and then solved. We were general, so you could do any transformation you wanted into a JuMP model, but it had to be a JuMP model. So now we've generalized that to what we call the transformation backend API, which enables us to transform it into what we call an abstract transformation backend, which can be anything. So it can be we have a default subtype for JuMP models, but we can also do other things. We've also recently added a backend for ExaModels, and we have a few other backends in place, like for instance for modeling toolkit and a few other things. So this has enabled us to have more ways of solving InfiniteOpt problems. We've improved our methods for direct transcription. So what's nice about InfiniteOpt is we have a pretty large library of ways to go about discretizing and solving these problems. I won't enumerate through all of them, but I think we have currently 26 different methods. We're still adding more, so if you have things you want us to support, we can add it. And these are pretty well efficiently implemented, so they scale linearly if we're problem size, so they're pretty minimal overhead to discretize. And we've added some better support for higher order derivatives, and we've basically improved the way in which we communicate the answer back to the user through n-dimensional arrays. This is getting a little bit to the weeds, but we can talk about it if you're interested. Along with returning back that information, we've made a little extension with interpolations.jl. So if you load that in now, previously when you solved an InfiniteOpt problem, it would return back to like a vector or an array of answers because you discretize, so it gives you back basically a discretized solution. What we do with interpolations is if you load that in, you can use either a constant linear or cubic interpolation to give back a function back at you that will interpolate over those discretized values you got, so you can have a continuous function to query your solutions. So pretty small add-in, but it's nice to use. The other change we made, I think this surprised Oscar the other day as we were talking about MathOpt.ai, is it turns out that we can't always use constants for bounds and start values for infinite variables because they are like trajectories or manifolds. So having the ability to have bounds that are like time dependent or start values that are like initial guess trajectories that are time dependent is very, very useful. So we've overhauled how we handle that, so you can now specify arbitrary Julia functions for bounds or start values. And with restricted variables, you can do that as well. And as well as when we define constraints, by default, they're defined over the whole domain of your problem, so all of your time horizon, all of your spatial domain. And if you want to restrict that to a subdomain, we now have this functionality called domain restriction, where you give it an arbitrary Julia function that gives a true-false for a particular time and position or whatever your infinite parameter is. And it can allow you to restrict the domain of that constraint. So this is very useful, for instance, when you're specifying boundary conditions for PDEs and stuff like that, where before we had to kind of hack around it, and now we have an interface that directly supports that quite nicely. We also have improved parameter support. So JuMP has made a few things lately with parameters with the MOI parameter objects that kind of inspired us to maybe do something a little bit smarter with parameters. We have parameters in two ways in InfiniteOpt. We have finite parameters, which is basically directly analogous to what you do in JuMP. It's just a single number or scalar. We also have what we call as a parameter function. It's essentially just a known function. It could be an arbitrary Julia function that you want to embed in your model. Could be like a set point or something like that. And so what we have now is we use the set parameter value from JuMP that allows us to update these. and we can update these in such a way that we no longer have to rebuild our backend. So we can have a persistent transformation, just do some minor updates, so we can try to keep our solver in memory and enable much more efficient resolves, which will become important in a few slides when I talk about NMPC a little bit. Along with that, if you're thinking about resolves, we also overhauled a lot of our abilities to do effective warm starting. So we have two functions we added. So we have set start values, which came from JuMP, which is a nice convenient way to take your previous solution and convert those into start values. Because we need functions, we require that you use that interpolations extension I mentioned before to get back a function to update your start values. And then it'll do all those updates for you. We also have a more advanced method you can use called warm start backend start values. What this does is, if you've already solved your model, it'll look at your backend and all of the variables it generated. It will update all of those in their duals for a better warm start. And it kind of keeps that in memory, so it's a much more efficient way of updating your backend model for warm starting. And so, where this becomes useful is we start thinking about an extension we have called InfiniteExaModels. So I talked about this last year at JuMP-dev. Kindly got an award for it. That was great. We've finally made our initial release of that, 0.1. We wanted to make sure it was just right before doing that, so we finally released that. It's pretty easy to use. So you just make your infinite model. You declare you want to use an X transcription backend with whatever solver. So here we're using the GPU version of MATNLP. You feed that in. And then we automate the transcription of your InfiniteOpt model to ExaModels directly. This dramatically reduces model creation time effectively to nothing on most problems. And then you can solve these very efficiently on CPU and GPU as it captures the recurrent structure of that problem. If you want to learn more about it, there's a link to the repository there. Or here we have the paper that we released on this earlier this year. And so here you can kind of see this is showing how, as you increase the number of discretization problems, so discretization points, increasing the size of the problem, how your solution time scales. And what we can see is the GPU implementation scales linearly and is consistently much faster than the CPU versions of the problem. We talked about this last year if you want to see more of that, but we also made the observation that even with this speed up, a significant amount of time spent in the GPU solver was just doing this initialization of the problem. So some symbolic factorization and spinning up the GPU kernel. That took a bit of time, and these can be used as one-off costs if you're going to do resolves with the same problem structure. Where that becomes useful, especially in chemical engineering, is with what's called nonlinear model predictive control. So we're solving a bunch of optimal control problems essentially in a loop with updates to our initial values and some parameters. So we've been working over the last few months on basically kind of optimizing this workflow in InfiniteOpt with resolves. And now with GPU, it's, to our knowledge, the fastest implementation of NMPC out there for a second-order solver. And so it's pretty easy. You just define your infinite model. You optimize it. You can use the warm start backend start values and update your parameter values that now are persistent. And so down here, we can kind of see the results. So if you do this in native JuMP, you can kind of see this base case for this distillation problem is 137 seconds. And when we do everything at GPU, we can get that down to 1.6 seconds. And then similarly with this PDE-constrained optimization problem, NMPC, the full run. And this includes solver time, setting up the model. It's the full workflow. We go from 143 seconds, and again, down to 1.42. So a dramatic reduction in time. And if we look at the solve times, we go from about 0.7 seconds per MPC iteration down to 0.01. So a pretty dramatic reduction in computational expense. And this is great because this means a lot of problems that maybe you couldn't solve fast enough to do in real time, we now can. So it's opened up the envelope for NMPC and quite a few more applications for us. One question that's come up, and this is mostly for Alexi, is how this compares to optimal control. They recently as well made an interface to InfiniteExaModels and GPU. So these are two Julia implementations to do optimal control that you could conceivably do for NPC. So I just thought I'd have one slide that kind of compares the differences between the two of those. So they're both, again, interfaced to ExaModels and can solve NMPC and GPU, but there are a few differences. So InfiniteOpt supports problems of ODEs and PDEs, whereas optimal control supports problems just with ODEs. We have discretization techniques on GPU that include finite difference and orthogonal collocation over finite elements, whereas optimal control only supports finite difference. One of them was broken, but I think we just got it fixed with a pull request, which is great. The other thing is InfiniteOpt, kind of based off the JuMP language, has the ability to facilitate set notation quite naturally. So on one of our benchmarks, which was the distillation problem, we were able to model it in 22 lines, but in optimal control, we had to enumerate all of the differential equations, which was 50 of those. So we get a much longer model. They do have like a vector syntax, but it doesn't quite capture some of the use cases to make it more compact. So by set notation, I mean, if you can imagine you have like a differential equation or some indexes over a set that you can use to generate a system of differential equations very compactly in set notation. Whereas it just wasn't readily possible with some of our case studies in optimal control, so you have to enumerate. So we have a distillation column of 60 trays. We have a differential equation per tray, and we have to enumerate the equations for each of those trays, which is a little painful. And then we support persistent solves, so we can keep the solver in memory and then not avoid those initialization expenses, whereas optimal control currently rebuilds the solver instance of every solve. And then what that ends up doing is if you look over the whole NPC run, the distillation problem, for instance, we take a little less than 2 seconds for the full NPC run, whereas optimal control took a bit more time. But with some of those changes, I think they could probably catch up as well. We could probably take questions at the end, yeah. The other thing we've done is, thanks to Oscar, is we recently made an extension to MathOpt.ai, which has enabled us to directly embed machine learning models into InfiniteOpt problems. The natural application that's first come up with this for us is being able to model neural ODEs in InfiniteOpt, which is really nice for some of our surrogate modeling techniques that we do. And it's kind of opened up the door for us to start looking into other types of machine learning models, such as maybe just a little more smart with Gaussian processes, and things like neural operators that map between function spaces rather than state spaces. Another thing we did, I talked about this a little bit last year, was we also connect to disjunctive programming. So we have infinite disjunctive programming. What this is useful for is it enables us to pretty compactly model switching constraints in infinite dimensional problems. So you can switch between different differential equations, for instance. So here, these are different right-hand sides of an ODE that we can optimally switch between. So each color shows you which mode is turned on or off. And so this kind of enables that kind of class of optimization problems. And we're currently developing some tailored solution approaches that leverage the structure of an infinite dimensional optimization problem in this context, so we can more effectively solve the resulting MI-NLP using potentially some GPU acceleration for the NLP subproblems. And more recently, Modeling Toolkit made an extension to InfiniteOpt. Where you can kind of take your model in Modeling Toolkit, maybe do a structural simplify, and then pass that on to InfiniteOpt, which they call a JuMP dynamic problem, but it's InfiniteOpt. And so that's kind of cool. There's a few little quirks of the interface. We kind of need to work with them to improve. They didn't really consult me when they made the interface. We need to fix a few things, but it's cool to see other environments starting to use InfiniteOpt as well. And so kind of going forward, some things we have on our roadmap, which we plan to add more features, of course. We plan to implement a few things that JuMP has that we've not added yet, like multi-objective optimization support for generic precision, complex values, stuff like that, which there's no fundamental reason why we don't have it yet. We just haven't had time to add it. We want to enhance our PDE support. So we currently mostly rely on finite difference, but we're looking to add support for finite elements as well to do other types of modeling that people typically do with PDEs. Also looking to expand the envelope of our persistent APIs where that currently just supports start values and parameter updates. We're maybe looking to adding and deleting constraints and stuff like that so we can do more to keep our persistent backend for more efficient resolves. Looking also with some of our GPU stuff, we're starting to look at dynamic parameter estimation problems and using GPUs to accelerate some of those problems with some collaborators we have. Also looking to expand the suite of support for with MathOpt.ai for machine learning models, exploring the use of neuro ODEs, maybe using things like neuro operators and stuff like that for PDEs. And also, we've had some initial work to kind of show it's maybe even promising to use direct transcription for actually training small to moderate size neuro ODEs, and we can show that has much better convergence properties than using adjoints. So we're maybe looking to use InfiniteOpt actually to train some of those models. And then also working with the infinite disjunctive programming stuff to come up with some more tailored solution approaches that are also GPU accelerated to more effectively solve problems with switching constraints. So I want to acknowledge a lot of people that have helped me over the last many years. Some of these are students, advisors, Oscar, funding agencies. So it's been a large effort over quite a few years, and excited to see where it takes us going forward. If you haven't taken a look at this or not familiar with InfiniteOpt rather, I'd encourage you to take a look and give us a star and maybe give it a try. So thank you.